Welcome to the first video in a series of videos about neural networks. In this first video we will explain how neural network works, and in later videos I will explain how it's trained, for instance. So in this first video we just have a trained network and we see, hey, what's happening? How does it work? So if we have a neural network, we want it to be able to do something, and the function I've chosen it to do is a XOR function. So let's have a little bit of look at the XOR function. XOR function is an exclusive OR function. It has two inputs, like input A and input B, and one output. And the idea is that if both of the inputs are 0, then the output is also 0. If one of them is 1, so A is 1 or B is 1, then the output is 1. And if both of the inputs are 1, then the output is 0. So it's really an exclusive OR. That means that it checks if A or B is 1. Okay. So I've made the network already, and I've trained it already, and this is the result. And we're gonna have a look at this network and see how it works. So the first thing to mention is that a network is made up of nodes or neurons. So all these little dots are nodes. And they can have a value. And in this case they can have a value between 0 and 1. And if the value is close to 0, then it's a little bit white or light gray. And if it's 1, it's black. And this neuron, for instance, is between 0 and 1. So these can be nodes, or they are called nodes or neurons. Okay, so the next thing to discuss is that we can divide this network up in layers. And it always works that we go from left to right, so from input to output, from left to right. And we start with the left layer, and we call that an input layer. And basically this is where you input your training data. So we want to train the network with something, test the network with something, and on the left side we have an input layer, and there the data is admitted. In this case it's only 2 nodes, but it can be 3 nodes, 4 nodes, it can be 800 nodes, it can be much larger. Okay, then the next node, not the next node, the next layer is the hidden layer. Again, this one can be much bigger, but also much smaller, so it can be equal to the number of nodes in the input layer, but it can also have less nodes, or it can have more nodes. It's all possible. And in addition, it can also be that there's more than one hidden layer. So that's also when we talk about deep learning, then a lot of times you have more than one hidden layer. The next layer, quite boring in this case, is an output layer. In this case it only has one node as an output, but again it can have a lot of different outputs, a lot of different nodes. The next part is the bias. So basically each layer, like the hidden layer and the output layer, also has one bias node, and that bias node is not does not change, so it's always 1. It's like an offset for the whole network, and it's yeah, that's it basically. What you already see that all those nodes are connected to each other, and it's connected with so-called weights. And the idea is that they all go from the left to the right. So this neuron, now let's say this neuron is connected to this neuron via this link. And it's a one-way street. So the information goes from this neuron, this node, to this node via the weight. And in this case I visualized it such that the thickness of the line indicates the value of the weight, so the thicker the higher. And if the color is red, it means it's a negative value. Okay. So then we're pretty close to having all the information. So please keep it in mind, and we'll drop them for now, and we will see what's happening if we give the 0, 1 as an input to the network. So the 0 and the 1, they are copied into the nodes. So the bottom node is 0, the top node is 1. And what's the next step? Well, we're gonna have a look first at the top node. That top node, so the 1, it will give its information via the weight as an input to the next neuron. And it goes via a very simple rule, just a multiplication. So the value of the node, which is a 1, times the value of the weight, which is minus 1.73, is equal to the input of the neuron. This is also applicable to the next node. So this node also gives its input to the top hidden layer node via the same rule. In this case, because the node is 0, there's not a lot of information transferred, it's just a 0. And lastly, for the bias, which is a 1, gives 2.33. So this means that the input for the next neuron, so, just to iterate, so it's nodes times weight, and the input for the next neuron is then 0.61. In this case, this hidden layer also has an activation function. This hidden layer nodes all have an activation function. And an activation function is something which translates the input of the neuron and the input of the node to the output. In this case, it's a sigmoid. I'm just going to show, let's see, yeah, there's my sigmoid. So it means that if the value is very negative, it is equal to 0. And if it's very positive, it's equal to 1. And in between, there's kind of a ski slope. Okay, so we have to input that 0.61 as an input in this activation function, and the output will be 0.6. In this case, pretty close to each other, and that's just a happy coincidence. So that's basically now this 0.6 is basically the output of the top node of the hidden layer. Let's do the same for the bottom one of the hidden layer, and we will have the same kind of multiplication, but now with a little bit different weights, and we will see that the eventually output is minus 2.83. We again input that in our activation function, and there we see that the output then becomes 0. So now the bottom node of the hidden layer is 0. Okay, so these are the outputs of those neurons, and what is the next step? Well, I think you guessed it already. We're going to do the same thing again, but then for the next layer. So now again we start with the top node. We give that information via the weight to the output, which is 1.7. Also for this one, it's 0, and it's minus 0.7. That all added together is approximately 1. And in this case, because I've chosen the output layer to not have an activation function, this is the final result in this case, 0.998. And this is basically how we calculate the output of a neural network depending on its input. This is only one possible input-output scenario, because of course we wanted to do the XOR, and the XOR also has as a possibility that the input is 0, 0. We do the same trick. Well, let's do it not by numbers but a little bit by feel. So this is all 0, this is all 0, so the input is here is 0, but here you've got a slight positive input, so this is like light gray, somewhere in the middle, maybe 0.4, 0.5 as an output. This node has this one has no input, this is no input because all these nodes are 0, so this is a solid 1. Okay, then we go to the next, the output node. Let's see, that's a addition of this node, this a little bit impact, and this one a little bit impact, and apparently these negative impacts here, because the weights are negative, compensate the addition, the addition of the top one completely, and the end result is 0. Okay, let's see what happens when we get the next one. Okay, here we see this path doesn't contribute anything. This one gives a little bit negative influence here, but this one gives a lot of positive influence, so this one is quite high. This one will be 0 because of this quite strong negative influence of this one. So this is quite high and 0, and here a little bit negative, so combining this will give 1. Cool. The last possible input condition is a 1 and a 1. Okay, what's happening? Both these two are close to 0, which means that this addition is almost nothing, this is nothing, and this one is left over, so close to 0. And that's it. So what we basically see that with the same weights, all these lines are the same, but with different input conditions we will get different results, which is exactly what we want. The learning phase is by changing these weights, but if a network is already changed, the only thing you change is the input nodes, and then you calculate all the subsequent nodes in the subsequent layers. Okay, and this is a XOR. I'm gonna show you now all the calculations for all these different inputs, and then you can see what's actually happening and how we really get those numbers. And you see that in this case the weights, so this is the weight column, and here also this is the weight column, they are all the same because it's the same network. What we did not yet discuss is how this network is trained. So how do we know what the right weight coefficients are? And that's the subject of the next video. I hope this was interesting, and have fun.